Recording in progress.
Good afternoon, everyone, and a warm welcome to Day 3, Session 1 FDP and workshop on artificial intelligence and machine learning in electrical engineering. I am Akshata M, Assistant Professor in the Department of Computer Science and Engineering at Vidyavardhaka College of Engineering, Mysuru, and I'll be your host for this session. Let me begin with a quote to inspire us. The beautiful thing about learning is that no one can take it away from you, by D.B. King. We are truly honored to have with us today Dr. Sharanya S., Associate Professor in the Department of Data Science and Business Systems at SRM Institute of Science and Technology. She holds a PhD from SRM IST and brings with us her over 12 years of teaching experience. Dr. Sharanya is actively involved as a faculty advisor and student counselor, also known for her strong communication and mentoring skills. She is currently guiding two research scholars and has published extensively in international conferences, reputed journals, and Scopus indexed book chapters. With such a rich academic and research background, we are excited to hear from her today. I now invite Dr. Sharanya S. to kindly begin the session. Over to you, ma'am.
Thank you so much, ma'am. Thank you for your warm welcome. And am I audible?
Yes, ma'am.
Okay. Okay. Is my screen visible?
Yes, ma'am. Yes.
Yeah.
No,
okay.
Not yet, ma'am. It is just saying that it has started screen sharing. Yes. Now it is visible, ma'am.
Yeah. Okay. Good afternoon for all the participants. And I extend my humble thanks for the organizing committee as well as for the ma'am for a very warm introduction. And okay. So now today I'm here to share my view about the digital twin and the AI integration in electrical infrastructures. So though I hold a PhD in computer science stream, my PhD is totally inclined towards multidisciplinary structures where I have done the predictive maintenance in aircraft turbofan engines and in bearings and things like that. Even I hold a postdoctoral fellowship from European International University and in the same domain. So now I think with no more waiting, we can just move inside the presentation. Okay. So now here, I'm just here to share my views about digital twin and AI integration with a focus to electrical infrastructures. So digital twins and AI integration is now prevalent or has become more common in almost all disciplines. It is not only inclined or it is not only confined towards the engineering, we can even extend to all the domains. All domains are now facing a great transference in their landscapes. It's mainly because of their AI integration only. So now, with that view, we are moving into the session. Okay. So first, let us now know about a very formal definition of a digital twin. Though we will get inside more details, first, this is a very formal definition of digital twins. There are numerous definitions, and this is one among that. A digital twin, it's a digital or virtual replica of any physical object. So the physical object, it need not be an abiotic, it need not be an biotic object or abiotic object, both living, non-living, any kind of infrastructure which is having some functionality can be transferred or can be converted, or it can have a digital twin of itself. So even the processes can be made as a digital twin. So the main purpose when we create a digital twin is we have to know the context in which the digital twin has to be created. So what are we going to twin? Twin is like a replica of something, which is what is existing. So when I mean it as a digital, it means it is going to exist as a virtual thing. So what are we going to mimic? So that's the main point in the digital twin. So a digital twin, it's an exact digital replica of any physical object or a person, system, processes, whatnot, anything. So it does the main purpose behind it is it should have a contextualized digital version. So in what context are we going to create a digital twin of something? So that's more important about the digital twin. So now, just this is an GIF which tells us how a digital twin will be. So you can see it's a motor kind of a physical object. That physical object, the features, the characteristics, or at least the outer things of the physical object, it's getting converted into a digital. It's getting all the artifacts of that object is being captured, and a digitalized version is being created. So that's what is the real digital twin. So now, when we are planning for a digital twin, to construct a digital twin, so what are the main parts, or what should be our main focus area? So that we generally call it as components. So first one, it's a physical asset. So what physical asset are we trying to twin, or are we trying to mimic? So that's the first thing. And the second one, it's the digital twin. So the digital twin itself, how are we going to create a digital twin? So that's the second component. And most importantly, the third component, it's the data. So always the data plays a very pivotal role in the construction of any digital twin based architecture. Why, wherever it is, if the data is going to play a very, very huge role. It's going to hold a lion's share in establishing the communication, or in establishing connection between these two twins. That is the physical asset as well as the digital twin. So you can see the data is acting like an interface between the physical asset and the digital twin. So any physical asset, the digital twin of the physical asset can be easily converted, and the bridge that is going to connect these two things as the data. So that's the importance of data. So with this definition and things, this picture would give a more clear idea of the thing. So here we have the physical twins. So physical twin is nothing but, twin means you should have two components. One is the physical component, other one is the digital component. So when I tell it as a physical twin, so it's on the physical infrastructure. It can be a building, it can be an aircraft, it can be an electrical infrastructure, or it can even be a human being. So that's the physical asset. And now in the digital twinning, what do? We collect the artifacts or the data, the characteristics, features, whatever we call, that data collection must be done. And that data, we will convert it into using some platform, some software infrastructure. We will be converting a digitalized version of the physical twin or physical object. So that's the digital twin. So the digital twin is the representative model of all the physical objects. So now, why do we go with the digital twin? So these representative models, why do we create it? So when we create a representative model, we have to create data management and data analytics facilities along with the digital twin, because we should have a purpose of creating a digital twin. So from the digital twin, we will be learning something. So that is being managed, or that is being explored by the data management and data analytics. So once we create the digital twin, what is the purpose of it is, we have to take informed decisions using the data, or using the behavior of by learning the behavior of the digital twin. So the information and the decisions of the digital twin will be captured, and the most important thing is, these information and these decisions will be given back to the physical twin to make improvisations. So that's the main point of creating a digital twin. So it's not the loop is complete, the loop is closed here, because it's not only we don't stop with collecting the data. We don't stop with knowing how the things are working. We don't stop with doing the data analytics, but we do focus on making informed decisions. So that informed decision and the knowledge what we get from the digital twin is given back to the physical world. So there lies the success of the digital twin. So now, why do we need digital twins? So first, digital twins are very essential for turning the data into actionable insights, as I have told in the previous slide itself. So just merely having the data, doing the analytics, learning the models, behavior, everything is not going to be a great success once that is not getting implemented to the real world. So the digital twins are very, very crucial for turning the data into the actionable intelligence. So to enable smarter decisions, operations, and maintenance of the real world systems. This definition is very generic. It's not that this can be fit, the digital twin can fit into any discipline. So that's the main thing. So now we'll see few application areas where the digital twins are very crucial. So first is for real-time monitoring. So for tracking the voltage, load, and other health parameters of any electrical, any mechanical equipment. So that is the real-time monitoring. It can be done using the digital twin. And the second very important application is the predictive maintenance. So for one example is prevent the transformer and cable failures proactively. So there are a lot of maintenance strategies we follow. So the maintenance strategies are preventive maintenance is there, proactive maintenance, reactive maintenance, and now we are in the era of predictive maintenance. So when we go with the predictive maintenance, obviously we need the integration of AI. So with the current data and with the current by monitoring the current parameters and by using the analytics and the AI models like machine learning, deep learning models, we will be predicting when this particular machine will fail. So that's the main point in predictive maintenance. Once the failure is known or the time of failure is known, then we can adopt predictive maintenance strategies so that we prevent the failure. So that is possible using the digital twinning. Next is virtual testing and simulations. So testing upgrades or faults safely in a digital environment. So likely just imagine a scenario where we have a greater vision of creating a new infrastructure. So we cannot go to the ground and directly build the infrastructure and test there because it's very it's not cost effective and it's also not safe. So in that case, we can go for testing the same infrastructure by creating a virtual model of it, and we can simulate all the fault cases or all the cases, whatever we want to examine. So that's the virtual testing and simulation. So that's possible using the digital twins. Next is system optimization. So system optimization, when we do any optimization technique inside the system, so obviously, for example, to improve the power flow, reduce the loss, anything. So when we want to make any small optimization into the system, that can be, its effect can be greatly studied or clearly studied using the virtual twins or the digital twins. Next is smart grid enablement. So grid, in constructing an electrical grid, it's a very extensive operation. And nowadays we are moving towards the smart grids. So smart grids for automation and intelligent energy management. So smart grids are mainly for efficient energy management, energy distribution. That's the main reason why we go for smart grids. But immediately we cannot deploy a physical smart grid. So it's always good to create a virtual replica of it, and we can visualize or we can at least envision how the things are working in the smart grid. So that's one of the potential applications. And the next very important thing is AI-driven decision making. So we can, when we create a digital twin, obviously, whenever we create something as digital, the lots and lots of data will get generated. So how are we going to deal with the data? So AI-driven decision making is one of the pioneering case or use case for creating the digital twins. So we can, what not we cannot do with the data. So the data is actually the king, which is going to drive the entire world, which is actually driving the entire world now. So the AI is completely based on the data. So when we have lot of data from the virtual twin, we can leverage that data for doing forecasting, fault detection, controls, or even for optimization purposes. We can very well do it. So these are some of the areas in which digital twins are very effective, or it is implemented in the electrical infrastructures. So now, going for the evolution of digital twin. So when we talk about the evolution of digital twin, there are 4 categories in which the digital twins have evolved. So the four things, on the basis of 4 criteria, we are going to cover the evolution. So the first is the definition, technology, scale, and the coverage. So the digital twin is still evolving. We are actually in the mid stage. We don't have very complex digital twins. We have very few only, that too at a very small scale. So initially, how did the digital twin started was we have statically updated simulation models. So when many of us will have the confusion when what we call it as a digital twin, is it not the simulation? So what is the difference between the digital twin and simulation? Yeah, we'll deal it in the later slides. So we have the statically updated simulation model, and from there we move towards a dynamic representation where we have the bidirectional flow of data. That is, the digital twin will be communicating with the physical asset as well as the physical asset with the digital twin. All the vice versa communication is possible. And with the integration of all those things, we just formulated a hybrid definition where we are going to bring all the physical entities to convert it into a digital twin. So that's how the definition works. And next, coming to the technology, earlier the groundwork was done using just simple PLM systems and simple simulation tools and platforms. Then these simulation tools were being integrated inside the cloud and edge computing platforms, and later more and more technologies came into the existence or came to help the digital twins, like mixed reality, augmented reality, virtual reality, and a lot of self-adaptive computations, AI models, of course. With all of these only, we are now in a advanced technological era where we can create very high-end digital twins. Then coming for the coverage. So coverage means in what are all the scales the digital twins can be used. So initially, the usage of digital twins, though the name was not actually meant as digital twin, it had a very different name. So it is done in the R&D departments, especially in the aerospace industry. So aerospace industry is one of the industry which is using more of digital twin systems. The reason is we know that an aircraft, when we build it, we cannot build the physical aircraft and allow it to fly. You have to have a digital replica of it, and we have to analyze so many parameters, the constructions, its health monitoring, everything has to be done. So the digital twins are very prominent, or it is finding its place in aerospace industries, especially the construction and the testing of aircrafts. So later it moved into creation of digital twin products, services, and the processes, and all both in the greenfield as well as in the brownfield scenarios. That's a very, very important thing to be noted. So it's not only with the assets what we are trying to construct from this scratch. It can even be implemented over the things which are already existing. So both of the things are supported by the digital twin. And later it had a different life cycle where we plan, build, operate, maintain, everything is possible using the digital twin. So nowadays, the coverage, it has an extensive coverage. Almost all the things can be mimicked. So that's the coverage part of the digital twin. Next, coming to the scalability. So scalability, it is like initially we had only few systems or linked with the digital twin. Now, with the wider technological ecosystems, everything gets connected. So the scalability, it has reached its peak point. So now also the digital twin is still evolving. We do have some extended applications in the later stage. So now we have a million-dollar question. That is, I'm talking about digital twin. Is it same as simulation? So now, no, it's different. That we know, but we should have a reason. So now simulations are a way to tell what could happen. So you have an equipment and you can just tell how the thing will work. And on the other hand, digital twin will even tell you what is happening and what will happen. So it is like an foreseeing. The simulation is like, okay, this is how it should work. But in digital twin, we can really see how is it working and how will it work. So that's why the digital twins are more powerful than the simulations. Lot of differences are there between the simulations and digital. I've listed only some four under the four criteria. So the first one is data source, which is very important. Simulation relies on predefined data, conditions, and assumptions, and everything will be static in case of simulations. So we cannot change anything dynamically, and we cannot see how is it going to work. So even if we are going to check with that, you will be allowed to do with only limited settings. So there you have a severe constraint in the simulation. But in digital twin, you can use the real-time data from the physical system and constant updation, reflection, everything is possible because digital twins always comes with the building of AI models. Next, the target and the simulation means it's only for a specific target. It's so confined. It's ideal for short-term analysis or just training purpose. But if you really want to know the real operation of a particular system in under all scenarios, all conditions, then it's better to go for digital twin because it has a long-term usage and even in extreme conditions, we can go with the monitoring, optimization, and all kinds of data. Next comes the cost and complexity. The simulation cost will be obviously it will be low, and the complexity is also it's less expensive. It's not a very big thing, and simulation is one-time building. So once you build a simulation system, we just use it. But in case of digital twin, it's more complex and expensive because it has to be dynamically updated. Every time a change occurs, then the digital twin, some updation will happen in the digital twin. So obviously, it is very complex, sophisticated, and it's not cost effective. But the cost, it's for the higher benefits it gives. And life cycle, it's a short term. Simulations are short term, and the digital twin is always focused on long term. So it's not bad, or it's not it's worthy to invest in the digital twins. And this is one picture which gives the technologies that are used in digital twins. Wherever we go, we have a creation of digital twin. We do it with the help of the technologies only. So now this is a physical entity, the data is a linkage for it, and the virtual replication. So now the digital twins are going to create a bridge between the real world and the simulation environment. So now when you see the data flow diagram, so from the physical world, the data enters the virtual world, and from the virtual world also, we have the data gets inside the physical entity. So this is two-way communication is the real power of the digital twins. So you can see lot of technologies in the context of AI and computing technologies. Most of them are computing technologies only. So all of these things are used in the digital twins. So cloud computing, reverse engineering, AR, VR, 3D printing, and even the simulation systems, AI, big data, data mining, visualizations, big data, machine learning, so whatnot, all the technologies are getting mapped into the digital twin. So when we are to construct a digital twin, we have to take the help of all these technologies or most of these technologies based upon the use case. So these are some of the prominent technologies which are used in the digital twins. So now, AI and digital twins building predictive intelligence for electrical assets. So now this is a very, very powerful combo. So because we are going to transfer the virtual replicas into active and intelligent agents. So now when we see the physical product and the digital twins are there. So the physical product's data will be given to the digital twin, or the construction of the digital twin happens based upon the data. And what is the digital twin giving us? Parameters. So whatever the parameters are there, that is being given to the physical product, and the parameters can be again changed. So now here we have a sensor which is going to act like a bridge to convert the physical parameters into a digital form. So that's the sensor. And here what you have is the AI, which is sitting at the back of digital twin, which is going to analyze the data, and with the data, it is going to give us the predictions and insights from it. So this is the combo of digital twin. Now, when you go for the digital twin, it's again, we have the sensor. The sensor will be capturing the data, and you definitely have to curate the data because the data will be available in a very raw form. You have to do data curation, feature engineering, and then we have on the real data, which is the predictive data, and with lot of critical parameters in it. So now with that, we have to perform the data analytics, and once the data analytics is ready, the insights of the data analytics will be translated into an actionable form. So and given to the operating system. So this is how the life cycle of a digital twin goes on. So from the real world scenario, we get the sensor data, and the translatable action insights will be given back to the physical system. So now this is actually the definition what we were seeing. So now why, or what is the capability of the digital twin. So now we have few questions to answer. What if we are planning to build a very remote system or a very intricate system, and where it's not possible for us to retrieve the physical data, physical operational data? And next, what if we have to assess the impact of future or unexpected events? So, violating the safety and integrity of the systems. So that's the second question. Or what if we want to analyze or study how the system will behave if we push the system beyond its boundaries, beyond the safety limits? What will happen? So all these three questions, the answer is only one, but we cannot do it in real time. The physical infrastructure, we cannot do everything in physical world because these will cause a greater disaster. So the answer for everything, it is the data. So the data is going to play a key role here. So first, when you create a digital twin, we get more than enough data. So by analyzing the more than enough data, we can easily get predictive insights. Next, this predictive data, it's not a mere data like a watch data or a time related data, just an image. No, it's not such a kind of data. It's a predictive data which combines a sensor input with a simulation. So now, when you get the sensor input, it means the real-time physical operation of the machine is getting into the play. Next, this enables decision making even in unmeasurable or in inaccessible condition. That's very important, because when you want to have an data from a highly dangerous site, you cannot deploy a human there. So obviously you can have digital twinning of it and you can do it. And now they do go beyond simulations. Digital twin is not exactly the simulation. They give predictive touch to the date, to the operation. Next is, it involves multidisciplinary simulation, generating intelligent reports, and the data analytics. So this is what we have, what we need to plan the future. So when we have to build a futuristic design, definitely we do want to know what is the drawback of the current design. So for that, digital twins are an excellent platform for it. So now we cannot tell whatever we conceive as digital twin is a digital twin. So that is a question that we should ask for among ourselves. So there are various levels of digital twin. So the first is digital model. So digital model means you have a physical object. The physical representation of that object is present as a digital object. So you can see, once prompted only, that is through manual operation only, these two things will communicate. Next comes the digital shadow. So this is the next higher level of the digital model. So where the physical objects, artifacts are being embedded or it's being propagated to the digital object, but the vice versa, it's not possible. It's not automatically happening. But in a real digital twin, the physical object as well as the digital object, they do a two-way communication. So the data, whenever it's necessary or in a very frequent manner, both of them do the communication. So that's the level of the digital twin. So now you can see there is no automatic exchange, and a more common example will be plans for buildings. A building plan, it's nothing but you create, whenever we plan for a building, we have a plan, and we have a physical plan. That's a blueprint of the building. So that blueprint, the building will be exactly constructed like that. But I don't think there is no communication between the building and the plan. And next comes the smart energy meter, which is a digital shadow. So in the smart energy meter, we clearly know that some physical phenomena is captured and it is being monitored. But is the smart energy meter giving something back to the physical world? No, it just depicts what is happening there. So that's a digital shadow. And the digital twin, it's nothing but a wind turbine simulation. So when the wind turbine is acting there, its simulated things is being presented in a virtual environment. So there you can see, you can even change the parameters, its direction, wind blade direction, or any other parameter adjustment can be done here. So that will be clearly mimicked, or it will be replicated to the physical asset. So that is what we mean it as a digital twin. So next is coming with the types of digital twins. So product twins, process twins, system twins. So these are all three types of twins. And the product twins is nothing but a small product can be created, a digital twin of the product can be created. Process means it's very common in supply chain management, where every time we can learn how the things are moving in the pipeline. So those are all the process twins. And the system twins, it's more complex because it do involve the integration of product and process twins, and based on some timeline factors, it's actually complex twin, and you have to have a clear understanding of the ecosystem in which you are going to create the digital twin. So for example, creating smart factories production line are some of the things. So now, electrical digital twin is just a replacement. So wherever you have a digital twin, in electrical digital twin means we are going to create a replica of electrical system. So the electrical system, we have live sensor data, simulations, and obviously the AI to optimize the faults and permissions. So this is the electrical digital twin. So the common components in electrical digital twin, the first thing is IoT sensors. So IoT's role in creating digital twin cannot be undermined. So AI, IoT, and the electrical assets, all three will be acting together to create a complete environment. So the IoT sensors are mainly used for capturing real-time current, voltage, temperature, anything, real-time physical phenomenon. So that's being captured by the IoT sensors. And next comes our AI models. So the AI models will be learning the data, or the data from the IoT sensor will be sent to the AI models. And this AI model will do an extensive analysis for predicting the failures, or for optimizing what is the best value for this particular parameter, and any such things, whatever we need, the AI model can do it, provided we supply the data right. Next comes our simulation engines. So this is also a part of the digital twin, electrical digital twin. So now here simulation engine, we have to model the dynamic behavioral changes under of the machine, of the equipment. So whenever you are going to change something in the machine, its behavior, its working should be visualized to the simulation engine. So that's the very important phase of an electrical digital twin. And later, this is an optional thing. If you are going for building an highly scalable electrical digital twin, and definitely you have to take the help of edge computing and cloud computing platforms. So this is for enabling remote access, control, and decision making. The data will be transferred to the cloud so that it's available wherever it is procured. So these are all very, very important components in the electrical digital twin. So in the electrical engineering, we will create a digital twin of any system for mainly for real-time monitoring, predictive maintenance, and performance optimization. So these are all the three important use cases for creating digital twins in electrical systems. So here you can see this is just the sensors or the hardware, the real physical things, and you have the software. And again, always I've told you that the bridge that is going to connect these two things is the data. So how you are accessing the data, creating the data, that's the middle, that's the bridge. So now, what are the various layers, or what are all the various things that we need for creating an electrical digital twin? So the first is the physical system. So the physical system, it's the real world equipment, any equipment we can take. So whatever we want to create a model, so that will be the physical system. And next comes our sensors and IoT devices. So these devices are very crucial because the choice of these devices, it completely depends upon the application. So if you want to monitor a different character, if you want to monitor voltage, then you should choose a particular IoT sensor. Or if you want to monitor vibration, then you have to go for accelerometers. So a lot of other, depending on the component, you have to physical component you're going to monitor, then that particular sensor has to be chosen. Next comes the data acquisition phase. So definitely the sensors are going to pour in a lot of data. So you should have a clear-cut platform like SCADA, PLCs, PMUs for collecting all the data in a more presentable or in an accessible format. So that's the data acquisition phase. Once the data acquisition is over, we have to create a digital model. So here I want to mention a few things. Digital model, it's not only the AI. So a lot of models are there. Since AI models are easy and it's more robust and versatile, we are going with the AI models. But you do have mathematical models and other simulation models are also there. So MATLAB, ANSYS, Simulink, these are all few very commonly used platforms where we have digital models. But the main difference between these two things is they are not dynamically adaptable. So that's why AI model is becoming more popular in case of digital twinning. And next, once your model is ready, the model will be recreating how the physical asset is going to work. So once the model is going to recreate that thing, it will be generating again loads and loads of data. So that data, using proper analytics and AI procedures, we can definitely detect faults, predict the failures, optimizes load distribution, find optimal value for the parameters, and whatnot. Everything can be found using the AI and the analytics. So this analytics will be giving you recommendations or the insights of what you have learned from that particular system or what the AI has learned from the data that is being provided from the physical system. So once that is known, next phase, it's the connecting the final connection between the physical system or the virtual system and the physical system. It's the loop closing procedure. So what is the loop closing part of the loop? It's the control and actuation. So based upon the insights, the knowledge that we get from the AI and analytics, we will be adjusting the settings or for example, inverter frequency related to anything. So based upon the insights, we can make adjustments in the physical system and prevent the failure or prevent the unfavorable things to happen, or we can do the control over the thing, control over its operation. So that's the main part. And another thing is you can have visualizations. So visualization is a very effective form of human machine interaction. So the visualizations will clearly tell how the data is proceeding. So that's also a part of the digital twin. We can create dashboards of all the physical processes that's happening using the data that we get it. And also the AI analytics can also be visualized. So visualization will be fitting inside both physical system as well as on the virtual system. So these are all the various layers in which we have to build the electrical digital twin. So now components, again coming for components. So first is it's a more clear view of what we have seen as an gist. So the first one is the physical layer. So here comes our real world electrical system. Any system you can take, all the systems will be lying in the physical layer, which is our physical infrastructure. Next, the physical infrastructure will be producing, or the operation of the physical infrastructure will be monitored, or it will be known to the system using the various sensors. Smart meters, relays, lot of things are there. Here I have given only few important things, smart meters, and these are all some of the things which will be measuring the working condition of your physical system. So these actually they are converting the physical phenomena into a digitalized version. So after this, we'll be having only the numbers and the data. So now onwards, we have to start working on the data. That's come the second layer. So now the second layer, once you have the raw data, it's the data acquisition and edge computing. So as I told, SCADA, Raspberry Pi, some industrial gateways and PMUs, PLMs, all of them are used for data acquisition. And edge computing is an optional part of it. So where instead of offloading everything to a cloud, you can definitely have an edge server inside the premises itself, so that you can have the decisions taken inside the campus, inside the premises. So that's what edge computing is going to facilitate. So that also comes under the layer 2. And next comes the layer 3, where you have the cloud or the data processing layer. So the cloud layer, so you can offload the data to a cloud server where all the processing can be done. So what is the main purpose is we can have or store historical data. So for example, this InfluxDB is a very famous time series data, and we can get that data for doing the AI simulations and for creating AI models. So lots of data will be pouring from the system. So we need an infrastructure to store the data. So that could be a cloud platform. So you can have the infrastructure as service and you can save lot of data in the cloud. And next, we can do power quality analysis like harmonics, voltage signs, everything can be done in the data processing layer. So you have the data processing can also be done at the cloud. Next is you can integrate with the current energy management system. So that energy management system of the particular area, the particular site can be benefited by getting that data, and the insights of the data can be given with this EMS. And next comes the digital model and the simulation. So the digital model can be created using the AI, artificial intelligence, or even mathematical models can also be created. So MATLAB and Simulink, we can create the digital models using the and ETAP, PS CAD, power system CAD, and ANSYS Twin Builder. So these are some of the digital twin systems that is already available. And what is the end request or end result of building a digital model and simulation is first is to do the predictive maintenance. So when is this particular component going to fail? Or is it working under a good condition? What is the health status of this particular equipment? Next comes the anomaly detection. So is there anything anomalous is going to happen? That is anything which is not normal is happening there. So that can easily be picked using this digital model. And next is transmission, power transmission. So how is the power transmission currently happening? Is the demand and the supply is being rightly matched? So those are all the things that we can learn from this digital model. So this is done using the AI and the predictive analytics. So the data, the digital model will be giving a data, and this is what we are going to do with the AI. So these are all the high-end solutions or the high-end formulation, which will help us to build the futuristic things. Next comes the data control and actuation. So here we know that once the data is given, once the models are being trained, everything is okay, we will be trying to control it. So we'll have a control over the existing systems. We'll adjust the things based upon the insights provided from the AI data. And next comes the visualization layer. So we'll have the real-time dashboards or even the fault location systems. So these will definitely help the operator to know what is being or what we are going to adjust. So it's a visualization. Visualization will help us to understand things better. So now we will be seeing few use cases of the DTs. So first, the flow of this particular thing goes through this way, you can see. So this is the digital twin definition. So how are we going to create a digital twin definition? Digital shadows can be there. So shadows are nothing but like a smart energy meter where only one-way communication is happening, or a virtual representation of a thing. These are all various options available. So bidirectional communication, physical asset and services data, everything. So when you combine virtual representation, bidirectional communication and the physical asset, you call that to be a three-element definition. And when you combine it with servers and data, it becomes the 5-element definition. So these are all the various DT definitions. So now, once those definitions are done, we can visualize these things, extended DT definitions. This is what we are going to visualize, or we'll be just focusing on one particular thing. We will be narrowing down. And next, we are going for the potential application part of it. So what is the application part of it? So you can see condition monitoring can be done, remote monitoring can be done. So it can be done even for the grid plant or a single unit or for a complete system or a complete ecosystem. Anything can be done. So depending upon the use case, we'll be choosing between remote monitoring or the on-premise condition monitoring. So this is the few application. And then we have a framework. Lot of frameworks will be there for the digital twins. Frameworks are nothing but the models, AI models. So based upon the models, we'll communicate to the potential application part also. And what happens here in the framework is that whatever the technology, whatever the data that we gather there, it is the data acquisition, modeling, analysis, lot of things will be done in the enabling technologies. So this data will be processed, and the end results of this data processing will be leading to the maturity of the next generation digital twin. So now you can just you can tick the check boxes. Are we considering the live data or multiple case scenarios considered? Is it a very generic framework or a specific one? So how are we going to build a digital twin? So this is how the digital twin has to be validated. So now we'll see few example digital twins. So the first one is it's just a case study only. So a lot of other forms of digital twins is also possible. Energy management using digital. So here you can see The digital twin actually presented here in this particular slide, it is the it models the energy consumption of any building. So here, what is the primary focus is you have to identify what are all the potential opportunities for energy savings and improve the energy management by monitoring the physical asset performance. And then we identify the by problems. What are the things which is going for or data energy leakage, anything. So that has to be identified. And this is a one comprehensive use case where you have to do maintenance part, you have to go for optimization, and you have to go for data gathering, everything. So here, ultimately, we have to reduce the energy consumption without by improving the energy efficiency. So here you can see this is the contemporary framework where you get the data and you have the simulations and where we have the horizontal and the vertical integration of things. And the sensor data, we will be giving it to the next higher level where we have the data insights. Here the AI models will be operating on. So it's actually a two-way communication. So between there, we'll get back the data so that we have all the changes being done in the energy management system. So this is the energy conservation system for a particular building. So now, how does it work? Whatever I told there, it's being elaborated here. So first, we have the IoT sensors, which will be monitoring the electrical usage, temperature, the health status of the equipment, and everything, environmental condition also. Next, the sensor data plus the historical data. Already we will be having the backup data. So that data plus the sensor data along with external inputs plus the engineering models. So the models, it can be AI models or even the mathematical models. So those models will be giving us three flavors of services. One is the visualization. So how is the energy consumption pattern going on and the load pattern, everything can be visualized. So that's one way of digital twinning. Next is simulation. So simulate what will happen if this is going to currently, if this is going to persist for 1 more hour, 1 more day. So in that case, we can go for energy demand. Okay, what will be the tomorrow's energy demand? That forecasting can also be done. And next comes optimization. So the optimization means load shifting, and you're going to you can just shift the load between the various control centers, and we can adopt predictive maintenance and everything. So now the data or the insights, what we do, it is again becoming a usage habits, and this is going to give a continuous improvement over the physical systems. So this is the complete workflow of the digital twin. Now, when we go for the digital twin for any predictive maintenance, here it's given as a wind turbine. So you can see this is the physical equipment, and now this is a digital model, digital twin model of the physical equipment. So this is being constructed using all the asset data, real-time data, context data, every data. So now in the digital twin, what we do is we will be collecting all these data. Once the data is being collected, we now with the data, it's actually rich. It has a lot of knowledge in it. So with the domain expertise, with the historical data, and with the AI models, we will be able to draw insights. And next, parallelly, we will be getting the analytics. So analytics is nothing but how the particular the patterns of the data can be easily visualized. So that's the analytics part of it. So this is one of the digital twin for the predictive maintenance part. So now, how do we know when there is a failure? So obviously, in the knowledge part or even in the analytics part, we can very well find what is the failure part, or what is the abnormal thing that is happening inside the wind turbine. So when that abnormality is sensed, so we can easily find, okay, a failure is going to happen. Next, IoT based using digital twins. IoT based systems, this is a power transmission system. We can see you have a power plant and the power is going to reach a home location. So you have lot of entities in between, like step-up transformer, high voltage transmission lines, and a substation. And again, from the substation, it has to reach our. So at every possible point, we will be monitoring or certain parameters. So using this IoT, and also from the cloud also, we'll get the control. So now you can see here monitoring parameters are what is the dissolved gas, temperature, partial discharge, lot of things are there. Everywhere we will be monitoring the parameters. So these are done using the IoT sensor. And here we can see the values are sent to the IoT cloud, and the possible decisions, what comes from the IoT cloud is the most important thing. Here you can see continue the normal operation, or carry out the maintenance plan, or carry out the outage plan. What is the lifetime? How long this will continue? So likewise, you can just get the values. So here you can see in the high transmission voltage lines. So you can see what is the decisions, adaptive protection setting, dynamic line ratings, and carry out the breakdown prediction. Because if there is some problem, you can see if the parameters is gas leakage, on and off cycles, you can see, then you have to carry out the maintenance. So based upon these things only, the decision systems will give it insights. So now, when we go for this, is very, very common and most it's a need of the hour, photovoltaic panels. So here you can see we need three things. One is the digital twin to estimate the output characteristics. So the output characteristics of a photovoltaic panel is very important for estimating the faults there. And next is residual vector. And residual, when we mean it as a residual, it's nothing but the measured difference between measured value and the estimated value. So that's the residual vector. And next, the evaluation part. What is the difference and how long can we permit this difference? So that's the evaluation part. So this is the PV fault diagnosis system using the digital. So now, as a last part of my presentation, I would like to introduce some few digital twins already available in the market. First is Azure Digital Twins. It's being developed by Microsoft. It's completely based on cloud, and it's for building smart buildings, factories, energy grids, etc. So now, the features of it is it has a spatial intelligent graph where we can do the space planning. So based upon the space, we can place our infrastructure, and that space planning can happen in this Azure. Next is digital twin object models. Even a small object can be modeled, and the computation is also provided. And one provision is that data isolation using multiple and the nested tenancy capability. So you can have multi-level data isolation. So it's not that all data will be available for all people. So you can have access restrictions there. And very importantly, it is being integrated with Microsoft services. So Azure digital twins are very popular. This is one of the screenshots where the spatial planning of the system, digital twin system. And next comes the Siemens Accelerator. It's being developed a part of the Siemens portfolio, and it's mainly used for manufacturing plant, industrial equipment, and energy system. So now the next one is GE Digital Predicts. So it's also Predicts platform. It's mainly focused. The GE is it's called a general equipment, and this is mainly for electrical engineering, power generation, wind turbines, grid optimization. All these things can be done. And now we'll dwell more inside GE because this is so context specific. So now the GE systems are being developed, or it has an integrated Humble AI. So Humble AI, what is the speciality of Humble AI is it will be fallback, it will make your physical asset to go back to the safe operating condition. So that is why Humble AI is very, very important, because as GE Digital Twin is mainly for electrical infrastructure, it can convert the electrical infrastructure to move to the safe zone. So the last one is design considerations or the challenges in the digital twins. So the first one is data related challenges. So we have lot of data. So when we generate the data, if the data is too noisy and and we know that the data integration, we are getting the data from heterogeneous sources, and the sensitive grid operational data, all of these are great big challenges. Again, complaints with the regulations. So any complaints issues, it will vary from region to region. So this is one of the important challenge that we have to combat. Next comes the modeling challenges. So the modeling challenges is, as the electrical system, it's very complex. So you have to model the complex system behavior, and the model validation is a great checkpoint for us. Next one is scalability. So you have to always check the scalability of things. As the electrical infrastructures will be expanding, the scalability is also a bigger problem. And extending digital twins to form components to large networks, it's a very big modeling challenge. Next comes computational technical challenges. Is the digital twin that we are constructing capable of doing real-time processing? And if you're going to adapt to a new technology, is it interoperable? What is the compatibility between them? Next comes the latency and bandwidth. The data transfer has to happen between the physical asset and the digital asset. So what about the latency, bandwidth, and other network considerations? And how is the synchronization happening between the physical and digital twin? So these are all some of the computational challenges. Next, the life cycle challenges. So how well the organization is adapting to the change, and the cost incurred for creating or constructing the digital twin, and the maintenance part of it, and adaptation with the already existing systems. The next very important is cybersecurity. So now we know that the data is getting flowed in an open environment, especially the wireless environment. Always we have a chance for the data to get tapped. And any cyber attack happening on this will be collapsing the entire system. So cybersecurity challenge is a very important thing that we have to immediately address. Next is, as of now, there is no lack of standards and the compliance with the industry regulations. So whatever we create, we don't have any validating things for the digital twins. So these are all the design considerations. Whatever I presented here, it is going to give you one overview of how the digital twins work, and this can be adapted for any engineering discipline. Here I have presented with the context of electrical infrastructures, and lot of scope for research is there within the electrical infrastructure, especially the cybersecurity challenges and the data challenges. So these are all two important things where we can focus more. So any doubt? I think from my part, the presentation is over. So if you have any doubt, the session is open. Hello, madam. Hello. Akshata ma'am. Akshata ma'am. Akshata ma'am.
Yes, ma'am.
Yeah.
Sorry,
I'm
I lost
done
my
with the
connection.
presentation, ma'am. And is there any queries? I'm happy to answer.
Security of the analysis of well, yeah. As I said, I was
Okay.
saying earlier that both the soil.
Ma'am, thank you very much for delivering such an informative and engaging session.
Thank
Your
you,
clear
ma'am.
explanations and valuable insights have truly enriched our understanding, and we are grateful for your time and effort you have taken to be with us today, ma'am. We would now like to open the session for any questions or comments. Participants, please feel free to unmute yourselves or type your questions in the chat box. We'll be glad to take them.
So the security ULDS ensures that if the soil and
Participants,
the combination, then we can decrypt the message.
you're open for discussion.
Like it is resistant against techno attacks because it has 2 layers. Anyone can have a decryption software. So you can have a decryption software, but when I send, if you get my file, you can't decrypt it because you have to enter.
Participants, if you're not able to post the question here, you can put it in the chat box.
Yeah.
Only there's one character error of in the combination.
The presentation like
The voices are not clear.
Ma'am, thank you. Thank you for your
Okay,
time.
okay, ma'am. Thank you so much for the
We think the
opportunity.
session was clear and they have no doubts on it. Thank
Yeah.
you for that.
Okay,
Ma'am,
ma'am,
there
I
is a
had
question.
Yeah, there is a question.
Yeah.
Can the concept of digital twins be applied to human organs like kidney? Okay, human activities, human activities are being created as a digital twin, especially using the gamification technology. I'm not so sure whether human organs can be done, because kidney, when you take an organ like kidney, it involves the integration of lot of other other
Listen,
organs
sir,
also. So it has to take the control of nervous system, circulatory system, respiratory system, and everything. So whether all of those systems is it capable of getting modeled? That's actually, it's a good question, but as of now, I am not in a position to answer that, because it's a very complex thing. Because whenever we work with healthcare systems, it has to be done with utmost care, because even a small fact cannot be taken for granted. But now actually the we are creating robots which can mimic certain features, not every feature of the things. Any small part of it can be done, because for kidney is not only an excretory organ, it does lot of other functions also. So when we are going to create a digital twin of that, it do require a lot of research. Maybe in future this can happen. Okay, working on organ aging. Yeah, definitely. Yeah. If that is going to done, it's like an RUL prediction, remaining useful life prediction, what we do in the engineering stream. So with this current parameters, we will be telling when this component will be failing. Yeah, definitely this part of research can be done. By monitoring these critical parameters of the kidney, you can predict the lifetime or the kidney failure. That can be done. This is similar to RUL estimation, remaining useful life estimation. Okay.
Thank you, ma'am. Thanks for your
Akshita, ma'am,
time.
thank you, ma'am. And I convey my thanks to Saib sir also, who has given me this opportunity. Thank you, sir.
Once again, good afternoon, everyone, and a warm welcome to Day 3, Session 2 FDP and workshop on applications of artificial intelligence and machine learning in electrical engineering. Let me begin with a quote to inspire us all. Education is the most powerful weapon which you can use to change the world. Nelson Mandela. It's my honor to introduce our distinguished speaker, Dr. K. Nagasujata, who brings over 25 years of experience in academics, research, and administration. She completed her BE in electrical engineering from Osmania University, MTech in power electronics from JNTU Hyderabad, and earned her PhD from Andhra University, Visakhapatnam. Her research interests include power electronics, drives control, renewable energy, artificial intelligence, and soft computing methods. She has published extensively with 30 plus journal papers, 25 conference presentations, and holds 2 main Indian patents, with 2 more international patents filed. She has guided 15 MTech students and currently mentoring 10 PhD scholars. Dr. K.N. Nagasujata has served in key academic roles, including Head of EEE Department, Deputy Director at UGC HRDC, and Coordinator for several AICTE, UGC, and MHRD initiatives, a Senior IEEE member and Fellow of the Institute Engineers India. She has contributed to over 30 national and international events as chair, convener, or guest. She has been recognized with prestigious awards like Outstanding Scientist by VFRA and Senior Women Educator and Scholar by NFED. She is also deeply committed to women empowerment and served as president of WAVE JNHUT. With this brief introduction, I now invite Dr. K. Nagasujata to kindly begin the session. Over to you, ma'am.
Thank you, ma'am. Thank you, Ms. Akshita, ma'am. And hearty congratulations for the entire team for organizing such a wonderful faculty development program. And I think is my screen visible?
Yes, ma'am.
It's not coming full screen. Are you able to see the full screen, ma'am?
Yes, ma'am.
Okay, done.
Ma'am, it's not yet.
Yeah, that's what I have shared. I don't know, it's not coming full screen. I have shared the, let me share once again.
Yes, yes, ma'am.
Is it okay, ma'am?
Yes, ma'am. Now it's
Are you able to see the full
yes,
screen?
ma'am. Yes. Yes, ma'am.
Yeah. Very good afternoon to all the participants. And today I'm going to discuss about the renewable energy forecasting. And I think participants are from different organizations and different fields. So I think if in my talk is related to purely electrical and renewable energy systems. And as already know, renewable energy, people also understand what is a renewable energy, and everybody need the topic. So you can, in case if you found any doubts, you can ask me. So as all we know, India is rapidly increasing. 1 second, just a second, please. Yeah, rapidly expanding its renewable energy, and government is aiming at 500 gigawatts of the
Hello.
renewable energy. Hello.
Yes.
Yeah, are you able to listen?
I had called you. Sorry, no mistakes.
Okay, so 500 gigawatts of the renewable energy per generation by 2030, and zero net emissions by 2070. And as all we know, India's energy mix is it's a combination of conventional and non-conventional energy generation, and now forecasting is very much essential. In recent years, Central Electricity Regulatory Commission (CERC) and various state electric regulatory commissions have issued guidelines for this forecasting methods. And why we need forecasting? If we know the forecasting, then only we'll come to the know about the demand, what we have to generate the power. So the amount of the electricity injected in the grid provides the system, penalizes the power plants to deviating the schedule. And as we know, renewable energy producers are required to predict and set a generation schedule to load dispatch centers. As of now, as per the CWA report, most of the states like Tamil Nadu and Rajasthan, they are generating the power up to 50% and 45% respectively from these in these two states in a renewable power generation. In renewable power generation, forecasting and scheduling is the main key needs in the clean energy sector. As we know, all we know, the renewable power sources like solar and wind both are inherently intermittent nature of the renewable energy. So that's why because of this intermittent nature of the renewable energy sources, forecasting and scheduling is very, very essential for maintaining the grid stability and ensuring the safety of the electricity grid. So now we will see what are the main themes, how it will forecast will be done, and how we will go for this all assessment using these AI techniques. So real-time assessment can help to mitigate the congestion issues in the grid, and moreover, grid outages can be avoided in the renewable energy forecasting are minimized. As all we know, many DISCOMs can efficiently meet their renewable power purchase obligations with accurate forecasting. And it helps better revenue realization as economic dynamic tariffs encourage the movement towards the cost reflective tariffs. Yeah, I think it's just to brief a renewable energy sources. As all we know, mainly the renewable energy comes from solar energy, wind, energy, and all these are sustainable and eco-friendly. So because it is FDP, I'm not much concentrating much in deep about the renewable energy sources, just giving you an idea. Uh, Solar energy, as you know, solar energy and wind energy. Similarly, we have hydro energy, biomass energy, geothermal energy, tidal and wave. So we have a 6 different sources of renewable energy. And the benefit, coming to the benefits of the renewable energy, they are environmentally friendly. So in nature they are available. So it reduces the greenhouse gas emissions, and they are sustainable, does not deplete natural resources. As all we know, the conventional sources like coal is vanishing, very limited, it is depletion mode. So like that, we don't have the problem with non-conventional or renewable energy. So we will have a sustainable energy resources, and energy security reduces the dependence on imported fuels. As we know, we will import the mostly this petrol and diesel from the other countries, which will reduces our country's GDP. So lot of the money will be invest. We have to invest in these particular to purchase these fuels. And then furthermore is the economic development. And if we go in depth of this particular utilizing renewable energy, so it will create jobs and promotes the innovation. And we have a opportunities. At the same time, we have the challenges also, because of the intermittency nature of the renewables. As we know, the solar and wind, it is completely weather conditions, so we can't this is one of the limitation and challenge we have. And other is a high initial cost to establish these particular renewable energy systems. Infrastructure and technologies can be expensive. Storage and transmission, one of the other major challenges, storage and transmission. So whenever we will see, when we are generate the power from solar or a wind, or when the generated power must be stored, because solar, it will be available from depending on the weather conditions. If it is in the summer, most of the time we will get more time. In a winter, a little less. And we know in rainy season, a little more, depending on the rain, we cannot able to intermittent nature of the solar. So all that particular generator power and wind also, always we should know, we don't know what is the wind flow direction and what is the velocity. There is a, so that's why always we have to store that particular generated power, which will generate from the renewable energy or non-conventional sources in storage system. Still, this is the challenge, how better we can improve our energy storage systems, and grid upgradations are also needed. These are the few challenges when we'll go for renewable power energy generation. So this is what whenever we have to forecast. So numerical weather prediction, NWP, models the national meteorological agencies, and it will give the weather report. As all we know, we will nowadays everybody is even they will get the alert in your mobile about the what is the prediction, what is the next week, what is the today, what is the this week or next month, like that. So we will get this particular numerical weather reports from the meteorological agencies. Similarly, we can get the data from whatever the data we have, that can be weather data also, meteorological stations will provide. Similarly, wind and solar plant data will get from the generating units. So all these come together, we can power predict systems at that particular vendors who they will collect the data. So we have from all this meteorological data, we will predict what is the power we can generate. So if we use the forecasting methods, this is what we can do a better way, or in a more probable way and efficient way. We can predict how much power we can generate from by this particular solar or a wind or any other renewable energy source, and from that we can, from that particular data we can predict very easily. So this is a simple renewable generating station. As we know, the first one is solar energy forecasting. In solar energy forecasting, as we know, numerical weather prediction and satellite energy and radiative transfer models is these are the techniques we will use whenever we will forecast a solar energy. So this we can use with the machine learning methods like LSTM, long short term memory, convolution network, and for PV output prediction, and use of the cloud cover or irradiance data, or we can go for a short term and day ahead forecasting approaches. So as we know, whenever we generate the power from the solar, so we need the temperature, irradiance, and what is the amount of the energy it is generated, all these. So that particular whatever the data we will get, we will give to the machine modeling method so that it will be tuned. Solar power is inherently variable, and it will changes from time, and even it will have a it has to face the clouds, fogs, aerosols, all these it won't we can say range, but not exactly how it may be, we can't say. So forecasting aims to reduce this uncertainty, but for perfect prediction is impossible. We can tell the range. Okay, I think sometimes we will listen on radio, and from weather report the rain will come, but maybe on the day rain may not be come, or sometimes there is a huge. So like that, it may exactly not a relative thing we will get. Focus on the proper holistic forecast and error qualification. So diverse methodologies. So no single best method is possible. So what we are doing is we have to approach the physical models like radiative transfer, numerical weather prediction to statistical AI models, machine learning, and everything we will use. Or we can use a combination. Instead of one method, we can use for hybrid approaches also. Combined with multiple techniques, yield the most accurate and robust forecasts. So when coming to the generation of the renewable power, as all we know, when we connect to the grid integration is a major challenge here. So the critical thing is because at different levels and different places we can generate. And now everybody maybe heard of the solar ghar. So the government is promoting rooftops and solar panel roof solar ghars like that. So in each individual unit will generate the power. The excess power can be sent to the grid. So the grid integration is very very important topic in this particular whenever we'll generate the power. So accurate solar forecasts are vital for grid operators to manage the renewable energy penetration and ensure the system stability. So that's why also we need all this forecasting, what the data we needed, how much we are generating, and how we have to meet the demand. So they enable the better scheduling. If we forecast, then it may enable the scheduling and management and reduces the need of the costly resource. Because we know one of the challenge in renewable power generation is a storage of the thing. So that if we predict do the predictive analysis and forecast of the data, then this particular energy storage will be reduced, and it will reduce the electrical tariffs. Next, coming to the wind energy forecasting. As we know, wind is intermittent and not dispatchable, and it ensures the accurate forecasting. And we can optimize the scheduling, minimize the power imbalance penalties, and reduces the operating resource. And this is also crucial for smart grids and energy market operations. So for this, to forecast wind energy, what we needed, again this also it needs the meteorological data like wind speed, direction. As all we know, the wind speed plays a major role. If it is more than 5 to 6 meter per second only, then only we can generate the wind. So that's where wind turbine can be placed. And at the place, what is the temperature, what is the humidity, pressure, and solar radiation. This is the data we needed whenever we have to forecast the wind energy. And the operational data, as all of we know, SCADA is needed. And location wise, what is the elevation it has to place, and what is the longitude and latitude, and what is the roughness. Similarly, numerical weather as per the NWP model data, weather model outputs, global forecast systems, and like European Center for Medium Range, they will provide this particular data. So this is a typical example of how we will get the data, or we can collect the data. So this is what historical. There are the various source. As last slide we have seen, different sites are there to provide the data. So NREL is the National Renewable Energy Laboratory. It will provide the data, but it will give the historical one. And MERA, it will give the reanalysis from that particular NASA. It will provide us the MERA, it will provide the data which will be long-term global data. So from that particular sites, we can get the long-term data. Similarly, in GFS global forecast system, it will forecast, it will provide the data which is from around 15 days, 0 to 16 days weather prediction will be done at that particular and available the data. Similarly, we have another available data is a open weather, and even IMD, India Meteorological Department, at our national level, it will provide us the local forecast and observations. And as all we know, SCADA will also give real-time data from wind turbine. So if we forecast the data, so we can at the real time, this is the power needed. So accordingly, we can integrate or generate the power from renewable sources. So to forecast, we need different horizons. So what is the horizon? We have suppose we have to, at that particular moment, we have to generate the power as per requirement. So in that case, what we'll call it as a ultra short. So in that particular, the time range is limited to seconds to minute. That's what this particular ultra short horizon we can use in real time applications, real time control. Short term, up to 0 to 6 hours. At that particular time, we can connect to the grid dispatch. So this is the demand during that we will predict the data. So whenever we'll predict the data, we'll have the information. Okay, this is a peak time. At the peak time, we need the data. That particular time comes under the category of the short term, and that whenever we have to dispatch to the grid, we can go for this particular short term. Similarly, medium term, up to 72 hours, a day ahead scheduling. So we have to do at that particular term, we will go for we will use the data for medium term. Similarly, we have long term vision. So whenever we need any maintenance or a planning in those time, we have to plan in well. So days to week time range, we have to go for the forecasting of the long term. So here, the features of the forecasting models includes wind speed and directional changes, what are the statistical features, and what is the weather predictions, and turbine curve for the wind generations. These are the features of the forecasting models. And this is what we will come across the wind forecast data set. It is a small data we have taken. Let us take a 10 minutes resolution. So at that particular resolution, for to explain all of you, we have collected the data from if you see 30th 6 only. On the 30th 6 we have taken the wind speed is 7.5 meter per second, the direction is 135 degrees, and the temperature is 22, and this is the 450 kilowatts. Similarly, at the after 10 minutes we have collected 10. So the wind speed, it is increased a little bit. 8 meter per second it became. The direction is a little deviation. If you can able to see the, you can observe from the data analytics, 138, and the temperature is reduced to 21.5. And further we have extended for 20 seconds, then it is again, then the wind speed a little bit reduced. So like this we can use, by using the SCADA systems, we can monitor all these particular data, and this particular data we can train, that we will see. So this is what we can collect the data. So there are several
Excuse me, ma'am.
forecasting. Yes, tell me,
Excuse me,
ma'am.
ma'am. Can we just go back to the previous slide where you showed the features? Actually, I was just recording,
Yes.
taking down the notes. Features, feature part. Yeah.
It's okay, ma'am?
Yeah, it was. Yeah, thanks. I'll just note down something and all the features.
Okay, 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 ma'am. Shall I?
Yes, ma'am. Please move on.
Yeah, this is the data what we will have, we will forecasting we require. And this is the statistical techniques, forecasting techniques are available. Statistical methods we have like auto-regressive integrated moving average, what we'll call it as a AMIEE, and exponential smoothing method. And these are the statistical method. We can club with present machine learning techniques like the random forest, XG boost, or support vector machine, like that. Or we can use even with deep learning algorithms, LSTM, CNN, GRU, and transformers. These statistical methods can be clubbed with whether machine learning or the deep learning. So that's what we can found in this hybrid model. AMIEE can be clubbed with LSTM or NWP with the machine learning. So we have all these are the some of the forecasting techniques as of now available, and it may improve a little bit next time also. So this is in whenever we'll forecast, we have to do data processing and tools what we use. So in data processing, whatever the data we will collect, that must be handled. So handle missing or outliers, and we have to normalize the data we have. After that, we have to resample the data. That's what we have seen in the simple example earlier. 10 minutes data only we have taken. So it may be from 10 minutes to 1 hour, or as we discussed, it can be for a few days, or long term, short term, medium, or long. So depending on our requirement, we will sample the data, then followed by the feature generation, what is the thing, and then it has to go for the train and testing or rolling windows. So the tools we can use for this data processing and model setup is, as all of you know, Python, or in Python machine learning techniques like pandas we can go for, our scikit or keras, or MATLAB, TensorFlow, and weather research and forecasting, WRF model. Any models can be we can use. So this wind forecasting heavily requires the data quality and variety. So the main, whenever we are going for this forecasting, we should need enough data. Without data, we can proper data, we cannot forecast very easily. So if we want to accurately forecast the data such as to generate the power as we require for the demand, so we need the quality of the data. Then we will integrate that particular data with the machine learning, or even we can go for a SCADA when data is critical. So for this, we have a future trends like transfer learning across regions are explainable in AI in forecasting, or real-time adaptive models. So this is a simple you can able to observe this particular graph. So this is what we have generated. This is the actual, if you observe, the x-axis is per 1 day, first 1 hour to 24 hours, and this is the power what we you can generate during the day ahead wind power forecast, and mostly what is the actual wind power, and forecast is you can able to see. And what is the power? It is hourly basis. So like this, depending on data, we can predict everything, and we can forecast. As for this forecast, we will generate. So forecasting reduces the uncertainty because the wind nature is very variable, it is intermittent, it will change, keep on, so it won't fix it at that time. So at that, for that, what we needed is forecasting primarily to the near term and prediction of the electricity generation from both wind and solar. So load forecasting, you can able to see if from this it is very clear, it refers to the prediction of the electricity demand. So we have seen the solar forecasting, wind forecasting, then other renewable forecasting is a hydro forecasting. As we know, hydro means we need the water, so we need the water resources. So what is the inflow and what is the precipitation, like that, where the dam is. The key inputs for hydro forecasting is the reservoir levels and inflows from rivers and precipitation, and what is the soil moisture, temperature, evaporation is water is, if it is flow, it will flow from far different places. Then what is the evaporation rates and what is the historical hydropower output and operational constraints. So these are the what key inputs we require whenever we'll go for hydro forecasting. So again, here also the forecasting horizons is 1 to 3 days, because earlier we have taken for hours solar, because the solar every day it will come, and it is available in terms of the hours. Maybe probably we may get around 7 to 8. The sun may okay, we'll get it around 6, but the irradiance what it can generate power, and the typically maximum we'll get from, we can generate the power 10 to 4, like that. So but when we'll go for a hydro forecasting, as we know, it needs lot of water, so the short term restricted to 1 to 3 days for operational scheduling, and medium term restricted to 3 to 10 days for so that it will be used for dispatch planning, and long term for weeks to months for water management and seasonal planning. This is how it will be helpful when we'll go for hydro forecasting, because I think everybody knows whenever all these crops and everything comes, then you are able to see they have opened the gate so that the water will go, the required water for the crops they will get, so like that seasonally, and how the water is, how much water is there. So for that, for every forecasting we need a long term approach. So these are again this hydro forecasting also. The statistical methods we have as AMIEE and regression models and hydrogeological data and machine learning, any of the thing, random forest or ANN or LSTM, or as a combination we can use for a hybrid models. And it must be with the data sources. So these are the challenges again we have in, because in every field we have, or every method we'll have a opportunity. Whenever opportunity is there, naturally the challenges are also there. So the challenges here is high spatial variability in rainfall, compulsory, because we need hydro means it's a natural resource. Once again, it is indirectly totally we are depending on the rains only, so high spatiality of the rainfall and complex terrain effects, data availability from upstream basins, and these are some of the things it is needed, dams and everything. And other, I'll go a little bit fast. These are only renewable introduction. So biomass forecasting. As we know, biomass we'll get from agricultural residues or forest waste, energy, crops, animal waste, and industrial biomass. So this is a typical pictorial representation of what biomass sources. Already all of you know. So for this also the key inputs are seasonal crop yields and agriculture. So all this will provide us the biomass. For forecasting, again, we need the yield models, as we discussed earlier in all the other methods. What are the methods? Statistical models. Similarly, we need the AML model, and here GIS and remote sensing. And because whenever we, one more other important thing in added point in biomass is a waste to energy management. Now it's a upcoming topic, and people, more researchers are concentrating in waste to energy management, because we can generate more energy energy from the waste also. Even if you observe this, people are buying waste, or municipal corporations, they are giving this particular waste to the power companies to generate the power at small scale. So forecasting horizons for biomass is a monthly or seasonal. Agricultural residues daily or weekly comes under biogas plants. So again, coming to the challenges of biomass, seasonal and spatial variability, lack of real-time field data, high transportation costs and losses, and socio-economic changes affect the crop and waste availability. So these are some of the challenges we'll found in biomass forecasting. So for this, even we know to forecast biomass, what we needed is a remote sensing, weather forecast, SWAT, and Python and softwares. Next, one more other major thing is a renewable energy is a geothermal. So as all of you know, geothermal, the power will be generated in the crust of the layers of the earth. So this is a pictorial representation from geoma, how we can generate the power. So I think, is it clear? I'm going a little bit fast because this is a intro part, and just revise that basic topics. I'll go a little, I want to concentrate a little on AI methods of forecasting. So this is the geothermal. And here forecasting for this, what we needed is a power production planning, grid stability, resource management, operational efficiency. So in case of the geothermal, the forecasting parameters needed is a temperature. That's what high temperatures it will be evolved in the earth crust, and steam pressure. That temperature will be used to pressure, and flow rate of the fluids, reservoir properties. So these are the statistical methods. As earlier we discussed, statistical methods, machine learning, physical based models, and hybrid models we can also use for geothermal. And these are challenges we have in geothermal forecasting: limited data, non-linear, and we cannot predict where we will get geothermal power or volcano. So it is a little challenging, and applications of the geothermal forecasting. Here in this also we can use the deep learning or IoT based and AI reservoirs. Similarly, one more we have is a tidal and wave. All these are the renewable energy power generations. So here key features are the tidal power, and these are the key features. Forecasting methods, as already we discussed. Yeah, please give me 1 minute time, 1 second. Yeah, I'm sorry. So these are what we can use in various renewable energy methods. So in case of the tidal and wave energy, we need the harmonic analysis and numerical models and time series models. So because it is very highly in tidal and wave energy, the nature of the tidal and wave is very intermittent. So that's why we require the harmonic analysis.
What's it?
So this is what overview of what we can generate and we forecasting techniques we needed for various renewable energies. All these particular renewable energy, whether whatever be the method, it will be uh, divided by the I think something is selected. I don't know. Are you able to? Is my screen clear? Some lines are coming for me. So this whatever be the method, we have to, there is a one commission called Central Electricity Regulatory Commission. So it will regulate entire the power generation and it will keep the data. So as per Central Electricity Regulation Commission, CERC, it introduced the deviation settlement and formed the regulations in the year 2014 and then started all this process. And these regulations were implemented to encourage and maintain greater grid stability and discipline on the part of the power producers and specified targets as much as. So what is the demand? So this is CERC regulations introduced in the year 2015 and forum of regulators are also published the model regulations and then it is carried to the next year. So from it is started what we have discussed all these particular renewable energy 6 different cases we have seen: solar, wind, then all the other methods one by one we have discussed. So that complete will be monitored by the CERC. So it formed in the year 2014 and 2015 then they published the other models and the regulations recommended by the all renewable energy generators forecast and submit their generation schedule on a day ahead basis either independently or through the qualified coordinated agency. On March 14, 2022, so then these regulations came into effect. There's revised the regulations and it replaced the regulations made in the year 2022 and 2023 again new guidelines because as new challenges are coming and if you see earlier to 1 decade back we don't know what is the renewable power generation to all common people. Now again if you go to any rural village also we can able to see the solar street lighting system. So like this major changes are coming in all these particular methods and day by day they are taking care. Government is initiating several approaches and methods to add on the renewable power generation and forecasting. So this is what actually if we have to go any of the forecasting method, so we have to go in we have to understood any of the AI techniques or machine learning techniques or deep learning we can use. So we have to from the data what we will do is we will train. Suppose if we are we have seen the several forecasting techniques. That particular technique, the data we have to collect from that collected data, again it must be for do the analysis, and accordingly we will generate the power, and it must be as per the regulation given by the CERC. So the again, as of now, it is added a new category of wind solar. You can, I think, all of you can visit the site of Ministry of Renewable Energy (MNRE) site. So you can able to see lot of the progress what we are able to generate the power and everything. And it also hiked the monetary incentives for both generators and procures to maintain the grid frequency within the safe range, because whenever we want the grid integration, so naturally it must be within near to our frequencies, the one of the major thing. So meeting the frequencies, so it must be around the 50 hertz. So that's why we have to concentrate on that. In the since 2016, and SERC of Andhra Pradesh, Assam, Bihar, and all these states, even Telangana, Tripura, Uttar Pradesh, they have issued the final forecasting and scheduling regulation. And other Delhi, Odisha, Uttarakhand also they have. So each state they have given their rules and regulation and forecasting of the data. If you go to the concerned sites of each state, you can get the data. So from that particular data, you can plus or minus plus or minus, you can take the generated expected forecast, you can do the forecast analysis, and then you can generate that particular power. So these regulations set a permissible limit for deviating, and at present there is an ambiguity of DSM regulations across the states, and there is no standardized permissible error band for deviation established across the country, and most of the states allow permissible error within the plus or minus 15%. So as if you see, as of now, they are generating the renewable power, and they are having a different tariffs yet to be focused more. So this particular for data, that means whatever the data we needed demand, and as we are producing the, or we generating the data as per the demand, so that everything has to taken care, because every state is having the geographical location is different, their sources are different, and their transmission from generating to transmission points are different. So there are so many factors are which included, so all these things plays a major role. So, however, few states such as Haryana, Tamil Nadu, and Tripura, they have a narrow range. They are error having only the plus or minus 10% as of now. We hope other states also will come under this. And for this, what we needed is still technological advancements and regulatory support. Achieving this error band is not always possible, and people are working on it to other. And if you go coming to the Madhya Pradesh, so Madhya Pradesh is maintaining only 15% of the stations are commissioned with the new regulations. And in August 2022, Karnataka Electricity Regulatory Commission, they issued the draft KERC about the forecasting, scheduling, deviation settlement, and related matters of solar and wind. And draft proposals were, it is a deviation of plus or minus 10% as instead of the plus or minus 15%. So whenever we have to generate the power, again we have to follow the, we have to think about the what are the state regulations, and whether we are able to meet that particular as per the demand or not. All these points are also very essential. And this is, as all we know, today nowadays we are generating the power. If you go any rural or urban areas also, you can able to see renewable power generation, whether it is a solar or a wind or a biomass. All these are available. A little bit less about the geothermal, but we are forecasting the data also from weather reports and everything. As of now, forecasting methods are also there. So because the topic is renewable forecasting, suppose if we take only one particular renewable forecasting, means we have to brief about all the methods, existing methods. So I gave a pictorial just representation of what are the techniques available. If we need to go in depth of the techniques, then again you have to go, or you can so many data is available on, and we have also several publications. If you anybody is interested, we are willing to share that also. So generation is there, demand is there, but we have to, what are the challenges in front of us? Because mostly some of you may are doing the research, and maybe you are guiding your scholars also. So if we focus more on the challenges, maybe we can uh, the barriers in front of us may be reduced. So that will be possible with the fulfilling our challenges, or accepting and founding the to found the solutions for these challenges. DSM regulations can be discouraging the renewable power generation uh, to at a slightly revenue loss, and particularly in states where deviation settlement charges are relatively high. Some states their tariff is very less, some states their tariff is very high. Even if less, maybe in at that particular point of time, the transmission from that place to our place needs a challenge. So like this, still we have a challenge. And this cost may be factored in tariffs by producing the renewable energy auction or in demand side. And if you observe, and most of you maybe know, whenever we'll generate the power from renewable source, whether it may be a solar or a wind, these or a biomass, this particular generation cost also includes with the storage. Even more researchers has to focus more on energy storage systems. And if we found the solution for energy storage, then only may the tariffs may be reduced. Not only storage, even energy management is also one of the challenge in front of us. So generation, anyway we are doing, not only generation, now I have to uh, get the quality of the power from this particular renewable power generation. Thereby how we have to improve, further improvement can be done with the grid, because the power we cannot use direct, all the power we cannot use. So whenever we are connecting this renewable power to the grid, that is also one other challenge we have. And to store the energy, we need better and most efficient battery management and storage systems are this. And this particular thing will be added if with forecasting methods and AIML, because data is available, we can predict that particular data. If we predict that particular data, we will generate as per we need. So the in like on the in our country, the demand side, India's complex grid system often experiences load shedding, high frequency variation, low voltages, high line losses, and making the assessment of the power a tremendous challenge. So if we concentrate on all these points, then only we can get a better opportunities. And still some challenges may exist further also, like weather intermittent nature of this solar and wind. And moreover, building capacity to transfer real-time information throughout the power supply is also one of the other key challenge. And as it necessary, power producers to modify this thing. And as all we discussed, grid operations and technical workforces need to be trained and kept to date with new technologies and developments in the forecasting space. Not only forecasting, and even maintenance of the solar cells. Other point people are again one more challenge we have is the solar cell, it is or wind fan, how the maintenance solar cell, it is there, the dust will be accumulated on the solar cell, then the power will be generation will be reduced. So how we have to maintain these solar cells? Similarly, when wind turbines, they will be placed very far, then maintenance of the fars, it will be affected by birds and whatever be the at that particular geographical location will have some of the disturbances, how to avoid. Still like this we have in every source with renewable energy, still challenges are there, but we hope we'll found the solution soon for all these challenges, and we are able to provide the power to the all consumers very less economical rate and with a good power quality. So this is what rest CERC also indicating irregularities with reference adhere to DSM regulations, and grid connected entities showed a tendency to overschedule, and consequently the system frequency has remained high for a significant period of time. So the way forward is again still the forecasting, and these are the some of the challenges we have, methods we have discussed, what are the forecasting, and forecasting of weather, wind, sunlight are accurately as possible. For that we need still advanced data, and to predict and collect the data we need the still advanced apparatus. Forecasting may be a challenge for new projects due to lack of historical data. So now we will see data is playing a major role, not only in power generation, in everywhere. One of the biggest challenge is a data theft and data collection. So I think everybody experiencing this data theft day by day. So if we further we have to go for this, how this data must be kept privacy and securely. That is also one of the thing if people have to think in that direction. Allowing the aggregation of forecast and deviation settlement at the boundary could improve the day ahead forecasting accuracy, and it aids the planning at the discom end. So this particular as of now it is available in the states of the Karnataka and Andhra Pradesh. So to reduce the cost burden of DSM charges, we have to implement already we have discussed this battery energy storage systems must be connected, and new business model could emerge that incorporate upcoming and advanced storage technologies such as green hydrogen, the next boom or era of the green hydrogen. And people, if you focus more on this particular green hydrogen, this may be the best solution for so many things. A simple implementation, if you observe this is the more frequent decisions reduced. If you observe this particular graph, this is for 1 day, time is for t plus 3 hours, t plus 1 day. So like this, if we forecast the data as per the forecast, we can generate within the limits. So how much we needed, if we have the information accordingly, we can plan to generate. So this is a typical example of forecasting. And even we can go for the centralized forecasting, enables the use of the forecast in unit commitment and dispatches, and it requires the generators and encourage the data quality, and it allows the greater consistency. Or we can go for a decentralized forecasting. So two methods we can go. Major role, centralized forecasting. This can be done by the system operator, or as we know, decentralized. This is what rooftop or solar car, everything comes under the decentralized forecasting. So it will be used by off-takers when making happens, and it will be limited scope and decrease the utility. So centralized forecasting by system operator supported by generator level forecast from plant operator, and it is of best practice approach. So these are the things what we needed for forecasting. Monitor the forecast quality. That means whatever the data we are getting, is it a quality or not, or improve the forecast quality is the better solution, and compare the quality of the different forecast systems. Final verification, error rates are not static. Yet we have to make some strategies like policy mandates, interconnection or market requirements. Power purchase agreements has to be modified, revised, and penalties. If we misutilize, we have to put more, we have to concentrate more on the penalties discussion also, rewards also, and partnership with the meteorological agencies to get the better data, third party vendors. And why data is needed to set up the forecasting? Static data we needed for all this. What is the latitude and longitude? What is the install capacity and training data? Further to train, we need the historical data. So this is the static data compulsory we needed. And the dynamic data we needed is a real-time generation, availability of the data, and meteorological data. Similarly, coming to the third-party vendors, the vendors use the proper priority of power prediction models, and they request the wind and solar data, and typical forecasts are selling at, as of now, this particular typical forecast is selling $200 per project or a month. Similarly, we have in-house forecasting. For in-house forecasting, we need all these things, whether we're working with vendors, what is the data they are having, what is the flexibility they are doing, whether the data provided by them is correct or not, everything we need. Because nowadays everything can be modified. We don't know what is the genicity, whether the data is genuine or not. So all these things are again threats. Similarly, we can go for all training of the operators and everything. Is it okay? Shall I continue? So these are the key takeaways. Forecasting which is needed, and better information we needed, interpreting forecasts, centralized and decentralized. So this is what renewable energy forecasting. The day wise we can forecast, or hours wise, or minute to hour. So depending on our availability or how we are collecting the data. So we have already discussed medium term forecast, short term forecast, or intra-hour forecast. So this is what we have seen, various methods how renewable energy will generate and it will forecast is needed. And accurate forecasting helps balance energy supply and demand. Advanced forecasting techniques like machine learning, artificial intelligence, and hybrid models, because these models, what it will do is it will predict the data. From the data we will forecast, and that will be used. Similarly, short-term forecasts enhance the operational efficiency, and long-term forecasts support the investment, maintenance, and policy making. And real time for all this needs the data. Integration of the real-time data, and tough progress forecasting method, we need it to be weather variability, data limitations, and system uncertainties. So for this, what we needed is data we have to collect, we have to generate, we have to predict. So for that, what we needed is a collaborative efforts are needed between the researchers, utilities, and policymakers, which are very crucial to standardize and implement effective forecast strategies. Yeah, thank you, one and all. So this is what we are having a various methods of renewable power generation, and how we can predict, followed by the what are the rules and regulation, and as of the state, what is the at present state, and few challenges and how to overcome, and what is the upcoming we have to do. Anything, any doubts? Hello.
Yes, ma'am.
Yeah, please.
Thank you so much, ma'am, for an insightful and thought-provoking session. Your vast experience and deep expertise has enlightened us, and we are grateful for the knowledge you have shared today. At this point, I would like to open the floor for questions. Dear participants, if you have any queries or thoughts, you'd like to share, please feel free to unmute yourselves or type them in the chat box. We'll be happy to take them one by one. Participants, the floor is yours now. If you're not able to speak, you can put the questions in the chat box. Participants, it's the last call now. Thank you, ma'am.
Okay,
We think
ma'am.
that there
Thank
are
you.
no questions.
Yes,
So thank
yes.
you so much for your time.
Thank you, ma'am.
Participants, you can leave the meeting now.